Okay, so great. Next we have Ludovic Gillet from here in Zurich, whose name has been mentioned a couple of times already yesterday in the context of he was the person who was really driving the early days of SWATH in our lab and continues to have a central role in DIA development in the lab. And so what you've also seen a couple of times in the last days, maybe some score distribution plots. You've heard people mention mProphet and so on, but we haven't really gone into a lot of detail about what this means, how the data are kind of extracted and scored, and how eventually the errors are estimated. So Ludovic is going to start with this this mostly on the scoring and so on, and then Isabel will take over afterwards and talk about FDR and alignment and things like this. So Ludovic, please.
No, hi everybody. Is it okay? Yeah. So yeah, so I will. You heard already from Mike the peptide-centric concept. I'm going just to re-summarize it quickly, and then I will show you some basics about how we do the peak picking, the scoring, and the fault discovery rate. So we stand now about here. So you've seen, I think yesterday, the data acquisition principles, how to make these assay libraries, or what we call now peptide query parameters. And you've heard this morning also from Mike how we do this chromatogram extraction, which is the concept of this peptide-centric chromatogram extractions of DIA data. And I'm going to focus today about the peptide identification. And so this is kind of a DIA acquisition scheme that you can see. Here, each of these red arrows corresponds to an isolation window. And you see that once you span all the mass range of your sample with a certain cycle time, as Mike mentioned, you basically cover the complete retention time and M over Z space of your sample. And what you can do now like this is actually you can select one of these mass range, for example, this mass range from 600 to 625. So this is what we used to call a SWATH. So it's the set of isolation windows that span the entire retention time. And if you put all the MS spectra acquired for that isolation window, you get a picture that looks like this. So maybe some of you are familiar with the picture here on the black background here, which is basically an MS1 map, where each of these features is MS1 precursor intensities of precursors in time and M over Z space. And here, this is what you have when you open one of these SWAS map or the MS2 maps from that mass from 600, 625. You basically get, again, a retention time axis. And here, this is the mass. But this is not anymore the mass of the precursors. These are mass of fragments. And as you can see here, as a very fast view, you see most of the things come as vertical bands. And as you can imagine now, if you understood the concept of the DIA acquisition principle, all these bands that come in a vertical shape like this are basically a fragment that originate from the same precursor. So the precursor was somewhere in that space between 600 and 625, was fragmented. And upon the fragmentation over the retention time, it gave rise to these fragments. And you see all these fragments here that coalesce, that they belong to the same precursor that was here. So this is the type of data that you have. So depending on how many maps, how many windows you acquired, you get 32, you get 100 such MS2 maps. And in each of these maps, basically the way we extract the data is by looking at these peptide libraries. And you basically have your peptide of interest. You have 5 fragments for those peptides that you know are fairly unique for that peptide. And what you do, you extract the chromatogram. So you extract these masses of fragments in the corresponding MS2 maps where the peptide is supposed to fragment. And then you extract it over the retention time. And what you get is basically this type of picture. So this is an abstraction. So for example, here, if you see, for example, the blue trace here that comes at 742, there's basically no signal at 742 here. And only at that place here, there is a signal that shows up. Then by chance, there is another signal that shows up around 45 minutes at this mass as well. And then there's pretty much nothing left until the end, etc. So you do this for the mass 742 for the fragment, 742 for the fragment 671, etc. And usually the concept is that you have most likely one place, if your peptide is present, where these 5 fragment on trace will coalesce together. And this will be basically the proof of indication that your peptide is present in your sample. So this is the type of data abstraction that we use, for example, if you're familiar with, if you come from SRM or PRM data. So this is the type of chromatogram that you see also in Skyline. This is what Brendan showed you. And this is one very important set of scores that I'm going to describe today. And the second set of scores are coming from the MS2. So not only do you have actually access to the chromatographic traces in the time dimension, but you can also open back the MS2 spectra at the apex of these peaks. And here what you can see, you can actually double check that the fragments are present, that the fragments are there with the right mass accuracy, with the right monoisotopic peaks, etc. So in this case here was even a heavy light label. So you can see that I targeted the light, but you see you also have a heavy peaks that comes together with it. So this is all the things that you can score in the chromatographic space, in the mass MS2 space. And this is actually the scores that I'm going to describe in the next couple of slides to explain you how you actually identify with certain confidence, with a certain FDR, the peaks, the peptides that are present in your samples. So basically, if you come from the field of SRM or MRM, you're used to see these chromatographic peaks like in Skyline. And in the past, when you were dealing with like 100 peptides in few samples, this was still feasible. You could open them all in Skyline and check by eye that the peaks were relatively reproducible at the right retention time, etc. But now here, when we switch to SWATH or DIA, we're speaking about tens or hundreds of thousands of peptides. And ideally, we now try to profile like hundreds or thousands of samples. So this type of data throughput is not anymore feasible to visualize by hand. And anyway, most of those things that you do visually is highly subjective. So we wanted to come up with a way to turn the peak detection into more automatic manner and to provide an objective peak quality scoring and also to assess the false discovery rate for the detection of the peaks. So this is this peak scoring and FDR assessment that I'm going to drive you through. So these are the type of data you might be familiar from Skyline. These are 5 fragments. You see a nice peak here. It's pretty much clear that the peptide is present in your sample. So here you can already intuitively guess some properties of scores that we will actually use. So you see here the peaks of the different fragmenti and chromatograms. They coalute very well. They have the similar peak shapes, etc. And they have a certain relative intensity, etc. So this type of chromatographic features, this I'm going to explain as well, which are very important for scoring these things. So sometimes, unfortunately, it doesn't look that simple. And in this case here, for example, it looks like we have a lot more peaks than expected. And especially here, you see you have 2 candidates. If you zoom into them, they actually look, both of them, pretty decent in terms of chromatographic coelution of fragments. And in this case here, one information, prior information that you can leverage is the MS2 fragmentary library that you acquired from your DDA data. This is what you have done yesterday. And what you see here, for example, the Y9 is the highest intense fragments. And if you compare here, the Y9, that would be the purple one, the violet one, that would be, for example, this one. So what you can see, you can use actually prior knowledge from former experiments, from libraries, in order to make sure that which one of the 2 peaks is actually the correct one. And this reflects, for example, in the dot product in Skyline, one peak has a clearly higher dot product than the other ones. So sometimes it's actually even more complicated. Dot product will not really tell you apart which of these peaks are correct from the MS2 fragment library. So in this case here, what you can use, you can leverage the, for example, if you have spiked in or heavy light labels like N15 or SILAC, what you can do, you can basically also check at which retention time points the heavy and light actually coalute together. In this case, it's a peak at 11.8. And then you can actually, even peaks that we were not sure in looking into 1 channels, because you have now the heavy and the light coelution as an additional validation and confidence of identifications. You can now be pretty sure that this is actually the right peak. So you have this, what we will call in the future, like plex scores, when you have multiplexing of heavy lights together. And sometimes here, like even the plex scores, heavy lights, they won't tell you anything. And in this case, the big question remains, how do you assess non-detectability of certain peptides in your samples? So this is something where actually also the decoys come into place. And actually, you can actually tell whether the peak is confident or not confident, and whether the peptide is present or absent from your sample. So these are basically the different criteria that you can intuitively already guess from the pictures I showed you. So these are the scores that we call intrinsic scores. So these are basically chromatographic scores, which check for coelutions of the fragments, peak shapes. You also, the coelution, so this is the retention time of the apex, basically. This is the peak shape score. So here you see the apex is similar, but the peak shape is actually different between the different chromatographic traces. You have also some intensity checks to see whether the peaks are of higher chance to have higher or lower intensities. We have extrinsic scores, which come from prior knowledge. So which are, for example, the retention time that we know from library retention time from your peptide. Usually you try to use also normalized retention time like the IRT scale. And also you have, as I showed you, the intensity correlation with the assay from your library in, for example, like a dot product score between the measured relative intensity of the chromatograms and the assay relative intensity from your DDA runs. And then you have these plex scores compared to heavy and lights if you have a spiked-in experiment. You have the non-label and the label, so you check the intensity correlation between the light and the heavy. You check also the same, the peak apex coelution between the heavy, light, and heavy, and the peak shapes of the chromatographic peaks between the light and the heavy. And in addition, as I mentioned, you also, this is also nicely visible now in Skyline. You can also open at any time the MSMS spectra at the apex of the peak that you think is the correct candidate for your peptide identifications. Then you check for the precursor mass accuracy, fragment mass accuracy of the different fragments. So this is usually scored in ppms, fragment monoisotopic. So you check whether you're actually selecting the monoisotope and not like a first or second isotope of something else. You check whether the fragment charge, if it's a singly charged or doubly charged fragment, whether this matches. You check also if you see additional B and Y in series, etc. So you have a lot more scores which are MS2 specific. So these are only scores which are accessible in DIA or PRM. And these are type of scores, for example, that you could not use if you are doing typically SRM experiments in the past. So again, as I said, getting these raw scores is fine, but it's not sufficient to ascertain the peptide identification. So I made a similarity to peptide that come from DDA. This would be like the raw scores you get from a sequence, like a X score, a SP rank. So these are the raw scores. But this usually, you know now that an X score from sequence is not sufficient to give you the FDR and to give you the peptide identification confidence. So now you convert actually these raw scores into FDR and Q values in order to actually assess also the real level of false discovery rate. And for this you actually need now to take into account that these events here happens by chance, and you need to correct for multiple testing hypotheses. And this is actually the concept also of decoys that we do a little bit similarly and with some differences as you will see in the next couple of slides compared to the DDA runs. So this is the concept of decoys that's used in targeted peptide-centric DIA extractions. So the idea that the decoys here are necessary to capture basically the quality of the peaks and the significance of the identifications. And the idea is that we generate this decoy sequence to make them non-natural, exactly like you would do a decoy database search based in shotgun analysis. And here it's very important that the decoys look very similar to your targets. So when the software scores the targets and the decoys, it should not make any distinction between both systems. So the idea, for example, here, like it's very important that your decoys that you generate from your peptide extractions, they have a similar Q1 distribution. So this is easy to understand. For example, if you have, the low M/Z range of the mass space is much more crowded, for example, than the mass range around 1,000 or 1,500. So the thing is that if you have a peptide that you extract at mass 400, don't take a decoy for it, which is in the mass 1,200, because then the chance of the decoys at 1,200 is very different. So you need to have a similar Q1 distributions. You need to have a similar Q3 distributions for the fragments for the mass of the fragments that you extract. You need to have a similar retention time distribution, same story as in the M/Z space. In the retention time space, you need also to extract your decoys around the same time where your target is expected to elute. You need to use the same number of transitions for your targets and decoys. So don't extract your target with 5 transitions and the decoy with 2, or vice versa. And you need to have also a similar relative intensity for the fragments in order for the scoring to work properly. So the idea is that you get a set of decoys which are looking like targets, but of course they should not capture anything real in your sample. So the decoys are generated in PRM and DIA by, as I will show you in a few minutes, by basically shuffling the sequence and just extracting those sequences from the data itself. In SRM, this was actually described in the paper from Lucas Reiter. In mProphet, the decoys need to be, for example, acquired during an SRM experiment in order to measure false transition and for false peptides. And this, unfortunately, here costs you some instrument times in SRM, while in PRM or DIA, you can basically just extract the data as you like. And again, the concept is that you want to assess the chance that this set of fragments happened by chance. And you will see that it has a very different meaning in terms of a decoy concept than what we do when you do a shotgun database search space. So this is a very simple example, can drive you through. So this is a peptide here that you want to look into your data. So the peptide has a mass of 642. So the only thing you need to know is that it will be present in the MS2 map 624 to 650. And these are 4 transitions of that peptide. And when you extract these MS2 maps for those 4 fragments, you basically see across the chromatographic retention time, you see basically the 4 chromatograms that comes up at a certain retention time, and you get basically a score for that peak. And the idea is that from that sequence, peptide sequence, you generate your decoy peptide assay. So here, in this case here, I show you an example with a pseudo-reverse sequence. Sometimes you can also use completely scrambled sequences. Here in this case here, because it's pseudo-reverse, you fix the arginines at the C-terminus, and the rest of the sequence is reversed. So VWID is written the other way. So of course, it's the same amino acid number of amino acids and same amino acid letters. So your mass of the decoy peptide is the same as the target peptide. But as you can see here, the mass of the fragments, so the peptide will be extracted in the same MS2 maps, but the mass of the fragments are completely different. Because you can count, the Y7 will be 1, 2, 3, 4, 5, 6, 7. So I think it's after the P here. So you have the mass PAVAGAR, and here it's also after the P here, but it's PEDIWVR. So the mass here of that fragment Y7 is completely different. So we keep the same fragments. And for example, here maybe the fragment Y7 has the one with the highest intensity, so we keep also the same intensity from the library. But of course, here now we extract the mass, a completely different mass than the mass of the fragments from the target peptide. So you extract these 4 fragments from these decoy peptides, and you also get the chromatographic pictures from these 4 fragments. And then the question is this, when you send this to the software will just try to find the best scoring peak, and it will give an output also a score for that best scoring peak, because it doesn't know whether that's a decoy or a target peptide. And basically what you can get from here is the score of the best scoring peak in that picture. And the score is of course lower in this case than in this. In the target peptides, so the target peptide will rather tend to be on the high scoring range, and the decoy peptides will tend to go on the low scoring range, etc. And then after you acquire and extract a lot of targets and a lot of decoys, you basically get this type of pictures that you're maybe familiar from the decoy database. But here are basically the distribution of the decoy scores and the distribution of the target scores, depending how you extracted them. So of course, sometimes the targets looks much better than the decoys. Sometimes it happens just the opposite. So in this case here, you see that the target peptide actually is barely visible. It's not visible, so the score reports the best scoring peak in that picture, which is basically very bad. So here the target peptide will actually be in the gray distribution on the very left-hand side here. While, for example, the decoy peptide here, just by chance, it happens that these 4 transitions that are not supposed to exist in your data just happens to find a peptide. Maybe it's one peptide, Maybe it's 2 peptides that coelute, we don't know, but it happens by chance that these 4 fragment ion chromatogram just happens to coelute relatively well in the middle of the window. And of course, for example, the relative intensity of the fragments is close to 1 to 1 to 1, maybe different than the one that you expect from the library, from the target peptide. But at least here the score is pretty decent. And this actually makes a decoy that scores pretty high in the decoy distribution on the right-hand side here. So this is to show you that once you acquire enough targets and enough decoys, you basically can plot the distributions of scores. And from that, you can basically learn what is actually true and not true in your identifications. So we do this for each of these mini scores. So each of these mini scores get basically replaced by one of these distribution histograms. So for example, here you see the peak-shaped scores. Here it's basically a dot product. Most of the targets here gather around the dot product of 1, while for example, the decoys, they have a relatively bad dot product. Same retention time, most of the retention time to the library or close to a delta 0 retention time. Well, for example, the decoys, they basically flatten out because they basically have a retention time completely random in the extraction window, etc., etc. So you get all these mini scores. You can actually assess which one of these mini scores is the most informative one. And of course, in order to make best of all those mini scores, you combine them by linear discriminant analysis, the typical LDA machine learning, where you can basically see that each mini scores by itself would be actually not sufficient. If you project on this axis or on this axis, the red distribution and the blue distribution would overlap very much. But if you use basically in this case here for these 2 scores, just this diagonal here, and you project on the green axis, you see really like the blue and the red nicely separates. And you do this in many dimensions for all these mini scores from chromatograms and MS2. And you basically get this type of profiles. Well, the machine learning tries to separate the best possible the true targets. These are the best scoring targets from the decoys. And by learning that, then you can actually manage to separate also the true targets from the false targets. And then you can see then the separation between your true hits identified and the false hits, which were not detectable in your samples. So the concept of these targets and decoys, which I wanted to show you, even though we generate them in a similar way as in shotgun proteomics, their statistical significance is very different. So this is the typical shotgun MS2 spectra that you can have in a DDA datasets, some of pretty high quality. And this type of high quality MS2 spectra, they have usually a very, very high chance to identify the correct peptide sequence from your target database. And as the spectrum quality decreases, you basically get more and more chance to get the decoy database, a decoy database hit. So, and you know that this kind of what I call the bad quality spectrum, which will recover a random hit across your database by virtue of this random hits, it will have 50% chance to recover the target database hit or 50% chance to recover a decoy database hit. And from that, you can basically, you know that you recover the FDR. And by getting the number of targets database, counting the number of decoys hits that you have in your database, you can actually calculate your 1% FDR. And then you can be pretty confident that you have a certain number of targets with 1% hidden false inside, which you can determine by using this decoy counting. So here, my point is that the spectrum here in DDA shotgun decoy database searching, the spectrum points towards either a target database sequence or a decoy database sequence. And here the decoys provide you a quality of an idea about the quality of the spectrum. And this is basically the chance that you have a random match between your measured MSMS spectra and this theoretically generated in silico spectrum. So the point is that the decoys capture the database search space and the search parameter complexity. And it doesn't really scale up with the number of spectra. So what I mean by that is that if you search one spectrum, it will extract at this certain precursor isolation width that you search your database with. It will extract a certain number of target hits, a certain number of decoy hits, and then it will try to find the best match between those subsets of databases. But if you search 1 spectra or 1 million spectra, the number of targets and decoys that you get for each match, for each test, will be the same. But what changes is basically, for example, if you put, instead of using a non-modified database search, or if you use a phospho database search, the phosphorylation will add a lot of search space in your target and will add also a lot of search space in your decoys. Both, they will grow in the similar dimension, but then the number of scores, again, will be the number of decoys rather captures the decoys increase with the search database space complexity. While, for example, if you do a peptide-centric DIA approach, this is a little bit different. So as I mentioned here, for example, you would have your peptide query parameters, your assay library. It's 40,000 target assays. So you extract those 40,000 target chromatograms. And then you also generate in parallel 40,000 decoy assays. And for these 40,000 decoys assay, you get also 40,000 decoy chromatograms that you also score. And here the point again is, you see here, the decoys here capture a very different concept. So the decoys here, they provide an estimation of the sample noise. Or, as I mentioned earlier, the chance that you get, by chance, coelution of those fragment traces while they're not supposed to exist in these samples. And what I mean by the sample noise is that you can easily understand that if you take a certain decoy peptide, the chance that you actually identify a decoy peptide that doesn't exist in a human lysate background is very different than the chance that you extract that decoy peptide in a water background. So if you have like 40 aquapeptides in water or 40 aquapeptides in human lysate, the chance that the decoys will actually be picked in the human lysate is much higher than the chance that the decoys will be picked in a human background. So this is all the point, is that the decoys here really give you an estimation of the sample noise, the sample complexity, and basically it will be very different than this concept of decoy database search space that you have in a shotgun type of data analysis. And here the number of decoys, you can also scale it up with the number of targets. In principle, as soon as you have enough decoys to get the proper distributions, you're already fine with this. But if you do this anyway, you need to take specially care about the multiple testing hypothesis corrections. So this is an example to show you also the concept of targets and decoys with a simple sample. So in this case here was, for example, a human lysate. And from those human lysates, we extracted a certain number of human peptides. And we also extracted a certain number of E. coli peptides. So we knew that those are false. You should not find these E. coli peptides in your human lysate. But it will just allow you to kind of see what's the balance and how this distribution change depending what you extract, the true targets or false targets. And of course, the decoys were generated by reversing the human and the E. coli, but in either case, they should not be present anywhere in your samples. So this is the type of data that you get if you get 20% human true peptides versus 80% E. coli false peptides. You see here the gray distribution here has a very strong component on the left, so on the bad scoring side. So this is basically this 80% of E. coli's make up that distributions. And the 20% human peptides makes up a low proportion on that side. If you have now 50-50, basically the distribution equalize each other. If you have now, if you reverse, you have 80% human peptides, you have a stronger component here, and 20% E. coli, a smaller component here. And if you have 100% human peptides, you get basically only the hopefully true peptide identifications. So the point I want to make here is basically, even you get 100% of true peptides that should be present in your samples, you see that actually the separation between the targets and the decoys is not perfect. So this has to do with like imperfect machine learning from the LDA measurements, etc. But my point is to make here is that if you use here like the typical naive decoy counting that you would do in shotgun proteomics, this would actually not work, because you would actually start counting here the targets until you get the first decoys inside. And as soon as you reach your 1% decoys inside, you will actually stop counting your targets. So here, for example, at 1% decoy peptides counting, you would say, okay, I stop here, but here actually you only identify 70 or 80% of your peptides, and you will actually miss all these peptides here, which are of course, low scoring, but that should actually still be present in your samples because you know that those are human peptides that should be present in your samples. And the point here is that, and this is all the concept of this multiple testing hypothesis corrections, is that the decoys here, you actually, these huge red decoy distributions, you should not consider it as such, but the point is that you need to scale it down, if you think about it like a scaling, until the level that it fits basically the false target sections of your target distributions. So this is actually, I don't know if you can see it on this picture, this is the dotted line here that you have in each of these plots. And you see here, you have to imagine that you scale down the red decoy distributions until it fits basically the gray distribution on the left side. So here, the scaling is, this is what we will call later, also with Isabel, something like we call pi 0, is basically the ratio that you need to contain false targets in your data. And this is basically, here the scaling is 50%, here the scaling is 80%, and here the scaling is basically 100%. And this basically, by scaling now the decoy distributions to nothing, you can actually realize that you can actually accept all the targets until the maximum, the lowest possible score at 100% without counting any decoy basically inside. So this is important in order to understand that we actually don't take those target and decoy distributions as they come directly from the data, from the software, but we actually do perform multiple correction hypotheses in order to scale basically these decoy distributions to match basically the false target distributions that you see on the left-hand side of these distributions. So this is in practice how we do that. So again, as I say, don't do, so here you can see the false targets and the true targets relatively well. So don't take the total distribution of the decoys and don't do naive decoy counting. Scale down the distribution of the decoys until it fits basically the false targets. And from that, then you can perform the P to Q value conversions. And this is done in the mProphet paper. We used the method from Story and Tipchirani that was published in 2003. And this is basically an histogram plots of the p-values. So if you would have only false positive, the p-values would basically be flat between very high scoring till the very low scoring. So these are the high scoring p-values between 0 and 0.5. So these are the ones that you can consider confidently as identified at 5%. And you can see here the p-values in case of decoys. So if all the assay would be false, you would have basically a flat distribution of these p-values. But if you plot actually the real p-value distributions of this type of gray target plots, you will see that actually the p-values of these targets, they tend to cluster rather on the good side, so on this 0, 0. So all these assays are identified within 5% identification rate, for example. And here, how you identify it, basically the level of false positives is by stretching out these asymptotes here, when you see actually the p-value here flattens out at this level, and from here on you can be pretty sure that this is basically the level of p-values that match only false positives, and you can extrapolate and actually calculate the number of p-values that you have in your first distributions. So this is basically what all the software do for you. They project this type of asymptotes. They calculate the p-value, convert it to q-values, and this is what you get when you get your final results. So everything is corrected, and you get basically an FDR estimation from your identifications. So basically the limitation of this machine learning, I want to comment on two things that you have to be careful when you start your first large-scale DIA experiments and your identifications. So the first is the limitation of the machine learning I mentioned before. So you need to combine these scores in the best possible way. And the way we do that is, for that you need to have enough good targets in your data. So this is kind of fine if you extract a lot of peptides. So if you usually extract a lot of peptides, you have a high chance to have always good and bad targets in your data. And this will be fine for the models. But for example, this starts to be problematic if you just look, for example, for exclusivity transcription factor in your DIA data. In that case, it might be that you don't have enough good targets for the machine learning to train and in order to differentiate the good and the false targets. And if the machine learning fails at the learning step, you basically get confusions between the good scores and the bad scores, and then a not optimal, a suboptimal kind of combination of scores for the final scores of your identification. So this is something you need to be aware. This is something also that Isa will comment maybe in the next moment about it. So now sometimes you can actually do the machine learning on the complete data set scale in order to kind of average good and bad targets from different runs, and in order still to extract and do a proper machine learning from the entire data set, and not penalize your data analysis on bad samples, for example. And there is also an important point here I want to make is don't remove the bad targets from your assays. So it would be tempting once you get this type of distributions, you say, okay, in order to increase my FDR, my number of identifications here, I'm going to remove all my bad targets from my library and just re-extract the same data again. And this is going to be wrong because in this case, you actually treat the targets differently than the decoys. And by doing this, you actually change basically the statistical power. You will see that basically the scaling of the decoys will not work properly anymore. You will not anymore get like a properly Gaussian distributions of the false targets. In this case here, basically, you will also start changing the statistics, and then everything that you calculate about the FDR will start to be wrong. So these are the two things you need to be careful when you do it. And the second is about the limitation of the FDR estimation. So as I mentioned before, we use very extensively this algorithm from Storer and Tibshirani. And this relies on using normal distributions. So when you look, and these are the type of plots you can now nicely get from Skyline, that I think you will do the exercise this afternoon. And I encourage you very much to look very extensively in these plots. So these are the plots of the distribution of the scores. These are the plots of the p-value histograms, as I mentioned you earlier. And from here, you can see whether the distributions you're dealing with are normal distributions. So this is the first hypothesis to apply this algorithm properly. And the second is that you should also use assays which are representative to your data. So here you should use the same number of transitions, as I mentioned, the same mass space, retention time space, etc. So the decoys should be representative. So if you have decoys which are not representative, you see that the decoys here will actually not sit on top of anything from the false targets. In this case here, you can actually picture that basically both the decoy distributions and the target distribution, they don't basically get this flattening as you would expect from these p-value histograms. In this case here, this is a sign that something is going wrong, and then that your decoys do not necessarily capture the false targets from your analysis. So this is something that you will see this afternoon, and I really encourage you to spend time, especially if you're starting with DIA analysis, in order to check whether the model worked, if your statistical analysis worked, if you can retrust your results. And yeah, so this is something now that you can nicely do in Skyline. So you can generate the decoys directly in Skyline. You can directly score using these mProphet models or different models. You can see the scores which actually have the strongest weight. You can see the scores that are actually penalizing. You can actually see these distributions in the models, in the p-value and q-value histograms, etc. So I really encourage you to explore these windows, as you will see that you can really see if your model worked properly. So this was just to give you the first step into this story about these automatic peptide identifications. You see that the identification scoring and concept that we use is quite different than the one that you have from the DDA database searching. So we use a target peak detection and scoring. We generate these decoys and we score the decoys the same way as we treat the targets. And then at the moment we do a per run FDR estimation. I say for the moment because you will see in the next presentation that we change slightly this criteria now. So these methods and concepts you can apply to any targeted chromatographic based data, SRM, PRM, any kind of DIA type of flavor. The concept is basically the one which underlies, as Mike mentioned this morning, all these peptide-centric type of softwares. So this was the concept that was generated for SRM with mProphet. Skyline, OpenSWATH, Spectral, PView, they all use similar type of concept, with slightly different way how to calculate the decoys, how to score them, but they all basically use the similar concept. And again, I re-emphasize the limitation of these algorithms. So the machine learning, be careful and check whether the machine learning has worked properly. The Q-value and FDR estimations use the proper decoys, and then check if you have a proper FDR estimations. And again, I re-emphasize that once you get your final list of targets, spend some time in Skyline, in PeakView to look into your data by hand and confirm that this is real, and especially if you have very low intense features, that you can actually see nicely your chromatograms and that you can see that the chromatogram disappears in your data. So this I still encourage very strongly, that you can still at the end manually inspect the data, and a tool like Skyline is really a great help for that. And again, this is the next presentation from ESA. So I mentioned here the limitations. So we have realized those in the last couple of years, and we actually worked hard to do a per dataset Q-value reassessment. We actually now try to insist on doing protein FDR estimations in order to cope for the creeping of false discovery rates. And then we do also advise to do a cross-run realignment in order to gain confidence in completeness in terms of your data analysis. So, and this will be touched by Isa in a second. And yeah, I thank you all for your attention. If you have questions, yeah, try to explain.
Thank you.
So you said that the decoys provide an estimation of the sample noise, but when you use a larger spectral reference library, you then have a larger decoy library, which ultimately then means that you have a harsher penalty when it comes to the FDR. So does that mean that there's a slightly different null hypothesis that we're testing, because it's not, you know, it does then affect the...
So you can very well imagine. So I mean, what we do, we actually model this decoy distribution. So whether you actually, you will have some software that have some tricks, like Spectrum, for example, doesn't extract one-to-one decoys. It extracts something like 10% decoys. So the decoys, basically the red bars, they come here. And as you say, if you use a big spectral library, you basically get a huge decoy space on top. But again, the point is that as long as you scale really your decoys, whether they come from low or whether they come from high, as long as you scale them really to the false targets, this is basically your corrections for multiple testing. So it doesn't, the size of the database doesn't affect so much the decoys. It rather affects, as you will see from Isabel's, it affects actually the ratio of false and true targets. This is actually the most concerning part. So decoys, they're usually fine. As long as you have a relatively good decoy generator that doesn't bias for anything, the decoys are usually fine. The problem is the ratio of false and true targets, and this Isa will comment heavily on that. Yeah.
So just to see if I've got this right, we're doing a linear combination of subscores, and then so that takes the one dimension and then LBA separate.
Yeah, correct.
So why are we doing the reduction to one dimension when we could do it in the higher dimension?
I don't know. Isa, do you want to comment? I mean, this is the usual way we used to, or George?
It really abstracts the problem, right? It makes it very easy to rank peptides, and usually we have a problem that different tools say that the signal is better or it's worse, and this makes it very easy for us to compute error rates and to satisfaction. And we can also use nonlinear classifiers for this ETH. This can also improve the situation for some scenarios, but we really like the LDA model because it's very simple and it's applicable to many problems.
Can I follow up? So have you tried more sophisticated models than LBA? Because I think that's, when is that from?
So the mProphet, the original mProphet was done for MRM data. That's why it's called mProphet for MRM Prophet. So it was retrained originally on MRM chromatograms. There was no MS2 dimension score. So this is something that we stretched basically to DIA originally. But I think if I'm, so we did try that when I was also involved in the PeakView developments, the very early versions of PeakViews from SciEx, and we tried different way how to combine these scores. But I think at the end we also switched back to LDA. I don't know. I think we were not refining. So the biggest difference that we find, This is also something that actually that I think Mike's group has implemented. So we do also like local decoys, which actually change very much also the way the targets are scored in the. So this is something that underlines peak view. So it's not so much the linear, the non-linear or whatever combinations you do on the scores. It's rather actually the way you treat the decoys versus the targets that, in our hands at least, seems to have changed the way you can extract more or less data. But
so a really nice thing about an LDA is that the numbers are somewhat, you can wrap your head around them a little bit.
Yeah.
You can essentially apply a simple linear equation to add them all up to recompute the score. When you use some more complicated models like a random forest or an SVM, whatever, you can sometimes get some very discriminatory power, but it's really hard to interpret whether or not you're overfitting or not. And so, so if you can use a simple model, it's often better. But we've used a support vector machine, but we've added a lot of cross-validation to ensure we're not overfitting, because sometimes we do.
Okay.
And I think there was a comparison, right, between, so Mike is talking about the tool from his lab, Percolator, and we plugged OpenSWATH recently into Percolator, so took away mProphet and rather plugged it into Percolator, which is using support vector machine. And my understanding is that the results were reasonably similar, right? Is that correct, Georgia?
The algorithms are closely related except in the classifier, right? And the results are almost the same. If I remember correctly, mProphet originally also investigated random forest models without this providing additional benefits. If you're interested in more sophisticated approaches, there's a preprint on bioarcsine about, I think it's called DIA neural network, where they replace the LDA by a neural network-based approach.
I mean, IPF that George developed regarding the phosphosite localization assessment is using a Bayesian network, right? So Bayesian models for scoring the localization. So it's
But we also make use of the
LD originally,
first.
yeah, and then Bayesian.
Other questions about mProphet? Yeah.
So you say that you have to be careful not to remove the bad targets, but if you have like a large library, say that was created for multiple tissue types, you know, brain, liver, kidney.
So you have too many bad targets, basically.
Well, but is a bad target just poor spectra, or is it something that you know isn't in your sample whatsoever, because that's going to affect
No, that's
searching for something that's not there?
so. You're right. So there is. I think Ben wrote a box in the library generation paper that we wrote when we try actually. So the bad sequence that you mentioned are coming from your library. So this would be a mistake from the DDA database search results. So these ones, then you need really to clean those in advance. So there you need to apply stringent FDR on your DDA database search approaches. Because if you have a wrong name on top of a spectra, even if the spectra is beautiful, you will identify it in your DIA data. But if the name is wrong, because the wrong name comes from the DDA approach, there's no way you can figure it out in DIA. There is a second level of false that we can actually now start to figure out is when the DDA identification is wrong because it's a chimeric spectra coming from two peptides. In DIA, you actually penalize them because you see actually these are two peaks and these are two different features. So these type of mistakes from the DDA, we can solve them in DIA, but the mistakes from the DDA identification, which is just a wrong label, on top of a true peptide, this there is very little we can do about it. So this is really something like you drag down from DDA, and you need to be very stringent with protein FDR on the DDA library to not to track those along to DIA.
But I think you're also referring to like peptides that are correct in the DDA library, but that just don't exist in the sample or not detectable in the DIA sample. So making this library larger. But I guess you will say something. Isabel will say a little bit about this, I think. Brenda, do you want to say something? you have one? All right.
Is there a big difference in what kind of method you're using to make your decoy? Because in Sky you have reverse sequence or shuffle sequence. Like an optimal way of doing it, or?
So we had, I think, so we tried, was it neutral? I think when we wrote the open source paper, we tried different models as well. We are revising each time a little bit differently. So I mentioned like the pseudo-reverse, we went to shuffle, and we came back to pseudo-reverse plus pseudo-changing of amino acids. I think the point is that you want to avoid really that you have super high scoring decoys. And the risk is that when you start to have a peptide sequence that looks like this, for example, here, when basically if by virtue of the amino acid sequence, the decoys here that it captures, for example, the four or five first letters here is actually capturing a mass because it's pseudo-palindromic from one side to the other side, you actually start to fall on top of the masses of the target peptides. Your decoy will actually capture masses which are not decoy masses, they're actually the mass of the target. So there are the proper retention time, there are the proper relative intensities. So then you start to get trouble, right? So all the point of these decoys checks that we try to implement is basically to try to be as safe as possible that the fragment ion that you extract as decoys, they are real decoys and not like potentially true from the peptides, right? So what some people do now, they even try to extract basically the mass of those fragments, not even in the same window, but for example in a different window, so or at a slightly different mass, in order to avoid that at least you fetch the target peptide as a byproduct of the decoys. But I mean, in general, as I said, so this you realize if you have super high scoring decoys here. But in principle, when you do like kind of a shuffling or like pseudo reversing, you're relatively safe, except few exceptions, as I say, which are pseudo palindromic. They're usually safe to use.
So one thing to keep in mind here is that I wouldn't say you want to avoid things with super high scoring decoys. If you have enough peptides, you're going to have by random chance.
Yeah.
Super high scoring decoys.
Sure.
You should, because you should reflect the actual normal distribution of your p-values. So the key thing here is that it should be an accurate reflection of the null hypothesis, right? And so and you want to make sure that you don't have things where your algorithm, either an LDA or an SPM, can learn the difference between targets and decoys. Because there actually are cases where you can actually do that. But anyway, those are just some things to kind of keep in mind. And the other thing often is it's good to train your model and compute your p-values or q-values from different portions of your data set. So things like Percolator do that. It actually uses cross-validation. So it uses 10-fold different cross-validation, and it calculates the SVM score 10 different times, and also keeps checking on a different portion of the data set that the p-values are overfitting or p-values are overfitting. It's just something to kind of keep in mind. There's a lot that kind of go into these thoughts, but in general, reversing or taking this last sequence, not the lysin or arginine, and moving it to the front tend to be the two best ways that we've found to.
Yeah, I mean, I think what Ludovic said though is that what you don't want is your target to look too much like the corresponding decoy, right? That's definitely not the case. Like that's a distraction for that signal, and so we found that with shuffling, actually this happens in surprisingly often. Like you have these poly A peptides or something, and shuffling them around doesn't help that much. So in our assay our decoy generator, there's a check to say does the decoy look too much like the target, and you can kick it out if you want. But now I think what Biognosis are doing are flipping like glycines and arginines, and this is moving like the whole precursor mass, and that's also an interesting idea. So I don't think it's totally resolved. It can still cause problems. Yeah.
So just on that idea, I mean, obviously you can search to make sure that if there is like a palindromic peptide, you can search to make sure it's there if it's reversed. But what about all of the non-unique peptides that we kick out of the library anyway? So all of those shared peptides, if we're reversing or we're shuffling, is it like,
What you mean?
should there be a blast that we do to make sure that we're not actually...
You mean shared like they're non-proteotypic, so they are shared across proteins?
Yes, shared across proteins.
So you're saying you could have a decoy that looks like another target? Is that what you mean, or?
Yeah, I'm saying that if you're shuffling or reversing, we're not blasting the sequences for our target organism. surely, you know, there is the potential that we could be getting quite real, legitimate peptides that are just, you know,
It's the same for DDA data, right?
Yeah,
so
yeah.
it's the same issue.
I think
don't know
this might come up
personally, so the non-single, so the non-prototypic peptides from the library, I personally never remove them out because I don't know. We have different concepts even within our group. Principle, those are peptides that come maybe from 10 proteins. Even if you quantify it, you might not know where it's coming from. But from the identification point of view, you can still identify it. It's usually pretty good because it's coming from so many proteins. So from the identification point of view, it will actually score usually pretty high in this picture. And then it's up to you then later on if you want to use it for quant or not. But I personally never remove them from the identification step. So I run them, all of them, through OpenSWATH. And only at the quantification step, when I'm looking at my table, I say, oh, do I want to use it or not? But that's a different question, right?
I think this might come up a bit with Alexi, actually, because this is a point he likes to talk about, is whether you in some cases can retrieve peptides that just kind of look like the thing that you were looking for. And it will also come up on Friday, I think, in the PTM session, because this is when this happens a lot, right? You have things that look very much like each other, but are only slightly different. And then we have can implement a second stage of scoring where you look at more fragmentines and try to really verify that the thing you're looking at is a thing you want to be looking at, which you may make a mistake with this kind of 6 fragmentine type of extraction.